Okay, chapter 16, we're going to talk about light now, light waves. So first of all, we're going to use the ray amount of light, so we're going to use like just arrows to represent light, but we know light travels as a wave. So really, light's got a wave, and it has a different frequency, as we know. But we're going to use a ray. So like if we look at light traveling through a prism, for example, we'll show refraction with this ray, how the ray bends and whatnot. The speed of light, or I'm sorry, sources of light. We know that all the sources of light that we have, natural sources anyway, would be things like the sun. Sun would be considered a luminous source. The moon and the earth are called illuminated sources then, obviously, because they don't supply their own light. They are simply reflecting the light that comes from the sun. Three terms the book gives that I don't know if we use it all, but in case we do: opaque, transparent, and translucent. Opaque does not transmit light. Transparent is an object that does transmit light, allows light to go through like glass. Translucent then would be an object that transmits light but with a blurred image, like a lampshade or something. Okay, the next two things you need to know are illuminance and luminous flux. Illuminance is the rate at which light strikes a surface. And we have a formula for that on the formula sheet I'll give you in a second, but the units on that are going to be lumens per square meter. And luminous flux is the rate at which light energy is emitted from a source like a light bulb. We have a formula for that as well, and the units are in lumens that we're going to use anyway. Okay, so here's an example then. Let's say we have a 100-watt light bulb. Here's a 100-watt light bulb. 100-watt light bulb emits 1,750 lumens. And so if I wanted to find the illuminance then, that's the luminous flux per square meter. So I'd have to divide by the surface area of a sphere at 1 meter away. Surface area of a sphere is 4 pi r squared. So I'd have to divide by 4 pi, which I've done here, which gives us about 139.26 lumens per square meter, which this unit right here, we're going to use LX for, lumens per square meter, and that's lux. That's in the book on page 433 if you want to read more about that. So you'll notice that this is an inverse square relationship again for light intensity at a certain location. And you guys are probably getting pretty used to inverse square relationships because our electric fields were inverse square relationships. Coulomb's law, the force between two charged particles, was an inverse square relationship. Newton's universal law of gravity was an inverse square relationship. Probably has to do with the fact that we're talking about per square area, and area is a square relationship with radius. So that's why these formulas involve an inverse square relationship, I'm sure. So here is our formula then for illuminance. The illuminance of an object is equal to the luminous flux, P. This is the luminous flux. The rate at which light energy is emitted from a source, divided by the surface area of a sphere whose radius is equal to the distance that we are away from the light source. So I put that on the formula sheet, and we can use that. Let's just do one quick example then. What's the illuminance on your desktop? If we have a 1,750 lumen lamp, that's 2.5 meters. So we're going to plug in 1,750 lumens in for the rate at which light energy is emitted by the lamp. And we're plugging in 2.5 meters in for R, and that gives us the illuminance, which 22.28, and that's lumens per square meter, or lux, LX. Okay, I recommend that you read about the first scientist to calculate the speed of light, especially the Danish astronomer who calculated the speed of light using the orbits of Io, one of Jupiter's moons. I think it's very fascinating. But he's one of the first person to calculate the speed of light fairly accurately. Here's the image of how he did it. All right. Another one is by Michelson in 1926. He measured the time it takes light to make a round trip between two mountains that were 35 kilometers apart and found a pretty accurate value for the speed of light there as well. And he won a Nobel Prize for it. I think it's pretty cool. I would take some time and read about diffraction as well and how it was first discovered. But here's diffraction of light right here, white light through a prism. And when white light enters a prism, it's separated into its colors, Roy G. Biv, the colors of the spectrum. So here are the frequencies of light right here. On the low end, you have, or I guess I should say the high wavelength, the low frequency, however you want to look at it. But the low frequency would be red, which has a wavelength of 7 times 10 to the negative 7 meters. And then the high frequency would be violet, which has a frequency of, or I'm sorry, a wavelength of 4 times 10 to the negative 7. And then I would be very comfortable with this chart right here. This is going to help you answer a lot of questions on the quiz and the test, and also your understanding of light. So we have primary colors. Primary colors are red, green, and blue. And if you combine red and green frequencies of light, you get yellow. If you combine blue and green frequencies of light, you get cyan. If you combine blue and red, you get magenta. Okay, so those are primary colors. The secondary colors would then be yellow, cyan, and magenta. The other term to know is complementary colors. These are two colors that add together to be white light. So for example, cyan and red would be two complementary colors. Because if you had cyan frequencies and red frequencies, cyan contains the frequencies of blue and green, and therefore, you know, this really equals blue and green frequencies. So together you get all the frequencies necessary to make up white light. Okay, color by subtraction of light then would be pigments. So a primary pigment is just the opposite. It's like a secondary color. Yellow, cyan, and magenta are primary pigments. And secondary pigments then are red, green, and blue. So a primary pigment like yellow is yellow because it absorbs blue frequencies of light. And so what's left then to reflect is green and red, which looks like yellow to us. So pigments is really color by subtraction, because if you have yellow, what's happening is the blue frequencies of light are getting absorbed, and what's reflected is the green and red, which looks like yellow to us. Okay, secondary pigments then would be red, green, and blue. Okay, the next thing is the polarization of light. Light can get polarized in one plane. Like for example, if you have water and light strikes water, the reflected image is often polarized. Much of the light gets polarized, and which means it's rotating a single plane of motion. I've got a couple polarizing filters that I can show people in class that you can see this effect, but this is where you would want to get polarizing sunglasses, for example, that block out that light that way, because that light that reflected looks like a glare, and you can block that out so that you don't see that using a polarizing filter. The last thing is the Doppler effect of light then. We do have a different equation we're going to, based on frequency here, and obviously we're dealing with not the speed of sound now, we're dealing with the speed of light, which is 3 times 10 to the 8th meters per second. And this is the speed of light that we're going to observe. So we're going to use this equation for our Doppler effect shifts of frequency, and we'll use this equation for our Doppler effect when it comes to wavelength. This is probably the one we'll use the most, because we'll talk about the frequency of light. Blue being the highest frequency and red being the lowest frequency. This is on the formula sheet, so you won't have to memorize this. All right, I hope this helps.